In this video, we're going to talk about how to find the domain of a logarithmic function. So let's start with the function log base 2 of x. If you were to graph this function, it would look something like this. It has a vertical asymptote of x equals 0, and the x-intercept is at 1. Notice that this graph, it never touches the y-axis, nor is it on the left side of the y-axis. So what this means is that x cannot equal 0, nor can x be a negative value. X has to be greater than 0. So whatever is inside of the log function is always a positive value. If you were to plug in log of 0, you would get an error. Or if you plug in log of any negative number in your calculator, you would also get an error. So when finding the domain of logarithmic functions, you need to set the inside part greater than 0. So let's work on some examples. Let's say we have this function, log base 3 x plus 5. What is the domain of this particular function? What we need to do is set the inside part, x plus 5, greater than 0. If we subtract both sides by 5, we'll get that x is greater than negative 5. And we can show that with a number line. So here's 0, negative 5 is to the left of it. Now x is not equal to negative 5, so we're going to have an open circle, but it's greater than negative 5, so we're going to shade to the right. All the way to the right, we have positive infinity, and on the left, we have negative infinity. Now, we're going to write the domain using interval notation. So we're going to read it from left to right. So it's going to be from negative 5 to infinity. So this is the domain of this particular function. Now, because negative 5 is not included as the answer, we're not using brackets. So we're only going to use parentheses for our answers, since negative 5 was not included. And you should always use parentheses when dealing with infinity. Let's say we have the function y is equal to log base 3 of 3x minus 5. Feel free to pause the video if you want to work on this example. So we're going to follow the same process. The stuff that is inside of the log expression, we're going to set it greater than 0. Now, let's solve for x. So let's begin by adding 5 to both sides. So we'll have 3x is greater than 5. Now, let's divide both sides by 3. So we get that x is greater than 5 over 3. Now, you can draw the number line if you want to, but there's no need for it in this example. We can simply write the domain as being 5 over 3 to infinity. So that's the answer for this example. Now let's try another example. So let's say we have y is equal to log base 3 of 4 minus 2 over 3x. So just like before, whatever is within the log expression, we're just going to set it greater than 0. So we have 4 minus 2 over 3 times x is greater than 0. So what I'm going to do is I'm going to subtract 4 from both sides. So I have negative 2 over 3 times x is greater than negative 4. Now I want to get x by itself, so I'm going to multiply both sides by the reciprocal of this fraction. So it's going to be negative 3 over 2 times negative 3 over 2. The 2's will cancel. 2 over 2 is 1. The 3's will cancel, and the two negative signs will change and become positive. So we just have x on the left side. Now, whenever you multiply both sides of the equation, or rather the inequality, by a negative number, the inequality will change direction. Now we have negative 4 times negative 3, that's positive 12, divided by 2, which is positive 6. So we get that x is less than 6. So here's 0, 6 is on this side. 6 is not included in the answer. If we plug in 6, this whole thing will be 0. So we have an open circle at 6. But x is less than 6, so we're going to shade to the left side. So reading it from left to right, the domain is going to begin from negative infinity, and it's going to stop at 6. So that's how we can write the domain for this particular logarithmic function. Now let's work on some more examples. Let's say we have the function y is equal to log base 4 of x squared minus 9. Notice that the base really doesn't affect the domain of the function. So regardless if it's base 2, base 3, base 4, it won't change your answer. What changes your answer is what's inside of the log expression. So we're going to do the same thing we did before. We're going to take whatever is inside and set it greater than 0. Now what we have is a difference of perfect squares. So we can factor this expression. The square root of x squared is x. The square root of 9 is 3. So we can factor x squared minus 9 as x plus 3 and x minus 3. The factor x plus 3 is equal to 0 at negative 3. X minus 3 is equal to 0 when x is positive 3. So these two numbers must be excluded from the domain, because when you plug them in, they will give you a 0 in the original expression. 3 squared minus 9 will be 0, regardless if you plug in 3 or negative 3. When you square it, they will both be positive. Now let's create a number line. For this one, we need to do this. So we're going to put our values that gave us a 0 inside the log. So we need to use open circles for those two numbers. To the right, we have positive infinity, and to the left, negative infinity. Now what we're going to do at this point is we're going to pick numbers in these three different segments. We're going to plug in those numbers. We can plug it into this expression or this one, depending on which one's easier. And we're going to see if we get a positive or a negative result. If we get a positive result, then that means that this expression is true. It's greater than 0. If we get a negative result, that means it's not true. That part has to be excluded out of the domain. So let's begin. Let's pick a number between 3 and infinity. Let's try 4. I'm going to plug in 4 into this expression. 4 squared minus 9, is that greater than 0? 4 squared is 16. 16 minus 9 is 7. 7 is greater than 0. So if we pick any number between 3 and infinity, this inequality will hold true. Now let's pick a number between negative 3 and 3. Any number. Let's try 1. 1 squared minus 9. 1 minus 9 is negative 8. Negative 8 is not greater than 0. So we get a negative answer, which would make a false statement for our inequality. So that part between negative 3 and 3, that portion must be excluded in the domain. Now let's pick a number between negative infinity and negative 3. Let's try negative 5. So negative 5 squared minus 9, is that greater than 0? Negative 5 squared, which is negative 5 times negative 5, that's 25. 25 minus 9 is 16. 16 is greater than 0, and it's a positive number, so this is true between negative infinity and negative 3. So you can write plus or you can write true. Either way, the answer will still be the same. So now we can write the domain, reading it from left to right. So we're going to start with negative infinity. It's going to go to negative 3. We're going to skip this part. By the way, if you want to shade it, it's going to look like this. We're only going to shade the parts that are true, or the part that we got a positive result. So we need to skip this section. We're going to write union. We're going to continue at positive 3 and go towards infinity. So that's the answer for this example. Now let's try another example. So let's say we have the function y is equal to log base 2 of x minus 1 squared. Go ahead and try that. So keep in mind the square will be applied before the information goes inside the log function. So you can view it like this. So the entire part x minus 1 squared, all of that is within the log function. So that has to be greater than 0. Now we know that x can't equal 1. If we were to plug in 1, that will give us a 0. So 1 doesn't work. And you could solve for it. Let's say if you take the square root of both sides, you're going to get x minus 1 is greater than 0. Then if you add 1 on both sides, you'll get that x is greater than 1. But that doesn't tell the whole story. Because when you take the square root of this, you also get the negative version of this expression. Now if we distribute negative 1, we'll have negative x plus 1 is greater than 0. Subtracting both sides by 1, we get negative x is greater than negative 1. Multiplying both sides by negative 1, we'll get positive x. Now we got to change this. Positive x is less than negative 1 times negative 1 is positive 1. So here we get that x is greater than 1, and here we get that x is less than 1, but x does not equal 1. So how can we show this with a number line? So first let's start with 1. We're going to have an open circle at 1. Now x, it can be greater than 1, so we'll shade to the right. And x is also less than 1, so we'll shade to the left. In other words, x can be anything except 1. And now we can confirm it. So if we go back to our original expression, or our first inequality, let's make sure that everything is accurate. If we plug in 1, we know this is not going to work. 0 is not greater than 0, so thus we have an open circle at 1. Now, if we plug in a number between 1 and infinity, let's say 3, this is going to work. 3 minus 1 is 2, 2 squared is 4, 4 is greater than 0. So we're good there. Now, if we pick a number on the other side, let's say between negative infinity and 1, let's try negative 3. Negative 3 minus 1 is negative 4. Negative 4 squared is positive 16, which is greater than 0. So that works. So it will be true for both sides except 1. So now we can write the domain as being negative infinity to 1. Now we have to pause at 1, so we need to recontinue at 1. First we got to put union, and then 1 to infinity. So this is the domain for this particular logarithmic function. Now let's move on to our next example. Let's say we have y is equal to log base 7 of x squared minus 4x. Go ahead and try that problem. So just like before, we're going to set whatever is inside the log expression greater than 0. Now for this particular expression, we can factor out the GCF, the greatest common factor, which is going to be x. X squared divided by x is x. Negative 4x divided by x, that's going to be negative 4. Now if we set this to 0, we'll get 0. And the factor x minus 4, that's going to be 0 when x is positive 4. So those are the two numbers of interest, 0 and 4. Keep in mind that x cannot equal 0 and x cannot equal 4. And the reason why we can say that is if you plug in 0 here, this entire expression will be 0. 0 is not greater than 0, so it doesn't work. Likewise, if you plug in 4, 4 minus 4 is 0. 0 times, in this case, another 0 times 4, that's going to be 0 as well. And so we'll have this case again. Thus, if you plug in 0 or 4, this entire expression will be 0, and it won't work. So we have an open circle at 0 and 4. Now, let's plug in other numbers. So let's pick a number between 4 and infinity. So let's plug in 5. Let's see if 5 is going to work. Five minus 4 is a positive number, and x is 5. When you multiply two positive numbers, you're going to get a positive result, which is going to be greater than 0. And so this works. Now, let's plug in a number between 0 and 4. Let's say 2. So this number is positive. 2 minus 4 is negative. A positive times a negative number will give us a negative value, which will not be greater than 0. If you want to get the exact number, this is 2, this is negative 2. So this is going to be negative 4. If we get any negative number, it's not going to be greater than 0. Now let's pick a number between negative infinity and 0. So let's try negative 3. So this number is negative. This is going to be negative. Two negatives will make a positive number. Negative 3 times negative 7, that's positive 21, which is greater than 0. So it's true for these two sections, but false for this one. So we're only going to shade the part where it's true. Now let's go ahead and write the domain, starting from left to right. So it's going to be negative infinity to 0, union. We're going to skip this part. We're going to continue from 4. So from 4 to infinity. That's the answer for this example. So that's the domain for this function. Let's work on one more example. Let's say that y is equal to log base 2 x plus 4 over x minus 4. Go ahead and try this one. So whenever you have a rational function, that is a function with fractions in it, where you have the variable on top and on the bottom of the fraction, the denominator cannot be equal to 0. So automatically we can see that x can't be positive 4. So we have an open circle at 4. Because we're dealing with logs, this has to be greater than 0. If it has to be greater than 0, we can also say that it must not be equal to 0. If you multiply both sides by x minus 4, these will cancel. You get that the numerator, x plus 4, cannot be equal to 0, which means x can't be negative 4. So we can put that here as well. So we have an open circle at negative 4. But now we can go back to our original expression. X plus 4 over x minus 4 has to be positive. It can't be negative. It has to be greater than 0. So now let's plug in some values to see where it's going to be positive. So let's pick a number between 4 and infinity. So I'm going to try 5. So we have 5 plus 4 over 5 minus 4. So 5 plus 4 is 9. That's a positive number. 5 minus 4 is 1. That's also positive. A positive number divided by a positive number will give us a positive result. Now, if we plug in a number between -4 and 0, so we have 0 plus 4 over 0 minus 4. 0 plus 4 is positive, 0 minus 4 is negative. A positive number divided by a negative number will be a negative number. And a negative number is not greater than 0. So this is not going to work here. Now let's pick a number between -infinity and -4. Let's try -5. -5 plus 4, that's a negative number. -5 minus 4 is also negative. A negative number divided by a negative number will give us a positive number, which is greater than 0. If you want to get, actual numbers, -5 plus 4 is -1. -5 minus 4 is -9, which is positive 1 over 9, and that's bigger than 0. So this is going to work for this section as well. So now let's write the domain as we read it from left to right. So it's going to be let's start over. -infinity to -4 union, and then we'll start up at 4 and go to infinity. So that's the answer for this example. Now let's try a similar but slightly different problem. Let's say we have y is equal to log base 9, and for this one it's going to be 2 minus x divided by x plus 3. Go ahead and try that example. So for rational functions within a log, we know that the denominator cannot be equal to 0. So x cannot be -3. And also the numerator can't be 0 because we can't have a log of 0. So if we add x to both sides, we get that 2 cannot equal x. So on our number line, we can take out -3 and +2. So let's put an open circle at those 2 points. Like before, we have -infinity all the way to the left and +infinity at the other extreme. Now, what's inside of the log must be positive or greater than 0. So let's plug in a number between 2 and infinity. So let's try +3. 2 minus 3 over 3 plus 3. Is that greater than 0? 2 minus 3 is -1. 3 plus 3 is 6. We get a negative number, so this is a no. -1 over 6 is not greater than 0. So let's put a negative there. Now let's pick a number between -3 and 2. The easiest is going to be 0. So 2 minus 0 over 0 plus 3. That's going to be 2 over 3. 2 over 3 is greater than 0, so yes, this works. We'll put a positive number there. Now let's pick a number between -infinity and -3. Let's try -4. So 2 minus -4 over -4 plus 3. 2 minus -4, that's the same as 2 plus 4, which is 6. -4 plus 3 is -1. -6 is not greater than 0. So that's not going to work. So the only part that works, that gives us a positive number, which is greater than 0, is between -3 and 2. So we're going to write the domain accordingly. From -3, stopping at 2. So because we have an open circle at -3 and 2, we're not going to use brackets. Therefore, this is going to be the final answer. So x can only be between -3 and 2 for this function. And of course, you can graph it, and you'll see that it will be limited by these values here. Now let's try this problem. Let's say we have y is equal to log base 4 and this is going to be x squared minus 3x minus 10. Go ahead and try this problem. So what we're going to do, like always, is we're going to set the inside part of the function greater than 0. So we have a trinomial with a leading coefficient of 1, and we need to factor it. We need to find two numbers that multiply to the constant term negative 10, but add to the middle coefficient negative 3. So this is going to be negative 5 times 2. Negative 5 times 2 multiplies to negative 10, but add to negative 3. So to factor it, it's going to be x minus 5 times x plus 2. So now we could set each factor not equal to 0. So x minus 5 cannot be equal to 0, and x plus 2 cannot be equal to 0. So x cannot be 5, and x cannot be negative 2. So we can put that on the number line. So here's negative 2, and here's 5. Here's negative infinity, and here is positive infinity. So we have an open circle at negative 2 and at 5. So now let's see which intervals work and which ones don't. Let's plug in a number between 5 and infinity. So if we plug in 6, 6 minus 5 will be a positive number. 6 plus 2 will be a positive number. A positive number times a positive number will give us a positive number which is greater than 0. That's going to work. If we plug in a number between negative 2 and 5, like 0, 0 minus 5 is negative. 0 plus 2 is positive. A negative times a positive number will give us a negative number which is not greater than 0, but negative numbers are less than 0. So that's not going to work here. Now if we pick a number between negative infinity and negative 2, like negative 3, negative 3 minus 5 is negative 8, so that's a negative number. Negative 3 plus 2 is negative 1, another negative number. Two negative numbers multiplied to each other will give us a positive number which is greater than 0. So we need to shade to the right of 5 and to the left of negative 2. So reading it from left to right, we have the domain, which is from negative infinity to negative 2, union, and we'll continue starting up at 5 and going to infinity. So that's how we can write the domain for this particular quadratic function within a logarithm.